Everyone. This is the last session of today's seminars, and our next speaker is Professor William Goldman from University of Maryland, and he's going to speak on locally homogeneous geometric structures on manifolds. Yeah, please.
Well, thank you very much for the invitation. It's a great honor to celebrate Ravi's 80th birthday. I've known Ravi, I think, since I was an undergraduate student here in Princeton, New Jersey, and when I think you were at Rutgers at the time, but I think you came to talk to Dan Burns and Steve Schneider, and later when I was a postdoc in 1980 and 81 and at the University of Colorado Boulder, Ravi was also there. We were
spent 6 months together, right?
That's right. And
Thurston Sullivan were there.
So we were part of a real adventure with them, Thurston and Sullivan, working, and we were learning about geometric structures and the geometrization of three manifolds.
Right.
Since then, we've seen each other in Indiana and New York and India and numerous other places. And what I'd like to talk about is some of Ravi's work from that period of time, the 1970s and the 1980s, on geometric structures on manifolds. His work has been a big influence on my own, and I'd like to describe a few of the highlights of where he made real seminal contributions. At that time, there had been some work. The subject began with Charles Ehresmann, 1936, who envisioned a program of starting with a topology, like a sphere, and asking what kind of local geometries can you put on it? Can you find a system of local coordinates in the geometry of a homogeneous space? So we take the point of view that a geometry, or a classical geometry, is the geometry of a homogeneous space of a Lie group. And local charts into Euclidean space, for example, where the coordinate changes are Euclidean isometries, defines a Riemannian metric of zero curvature. And a theorem which is can be proved in many different ways is that the two-sphere does not admit a Euclidean structure. So this is a theorem that we can explain to non-mathematicians easily. There's no metrically accurate atlas of the world. On the other hand, the torus, different topology, admits a lot of Euclidean structures. And this interplay between geometry and topology is what I would like to discuss today. In particular, we'd like to know when a topology, like a closed surface or a three manifold, admits a geometry of a fixed homogeneous space. So the point of view that I want to take is goes back to Sophus Lie and Felix Klein in 1872 in the Erlanger program, that a geometry means a homogeneous space of a Lie group. So Euclidean geometry is the Lie group. The homogeneous space is Euclidean space, and G is its group of isometries. So we've already described that. That's in more traditional differential geometric terms. A Euclidean structure is a flat Riemannian metric. And an example of a classification is, or the theorem of Bieberbach, that a closed Euclidean manifold is a quotient of a flat torus. And one can get a moduli space of Euclidean structures on the torus, which is going to be the space of lattices in Euclidean space. And this moduli space has a rich geometric structure of its own as a locally symmetric variety. And this is very similar to the classification of Riemann surfaces by Teichmuller space and the Riemann moduli space. However, the Riemann complex structures are not examples of Ehresmann structures, because although the coordinate changes are complex analytic and have analytic continuations, they're not globally defined. And that's an example. That's one of the key reasons why one of the key features of this class of pseudogroup structures. So the pseudogroup consists of it's a pseudogroup as a way of defining coordinate atlases on manifolds, and in this case, these are ones that arise from the restrictions of transformations of the Lie group G on the homogeneous space X. Another example, which I'd like to discuss in this talk today, are hyperbolic structures. These are geometric structures that are modeled on hyperbolic space and its group of isometries. And therefore, by the same construction as in Euclidean space, one gets a natural Riemannian metric on a manifold with a hyperbolic geometry. But this Riemannian metric, as in the case of Euclidean geometry, it has a large group of local isometries and can be used to define geometric structures in the sense of Ehresmann. In particular, all such manifolds, if you assume compactness or the notion of geodesic completeness, these are all quotients of hyperbolic space, where gamma is a discrete group of isometries, and that will necessarily be a group that acts properly on hyperbolic space. Whenever you have a homogeneous Riemannian manifold, any discrete group of isometries will act properly. Properness means that the quotient is Hausdorff. It means that the map defined by the action from gamma cross X into X cross X defined by the action is a proper map, which just means that if you go to infinity in the group, you have to go to infinity in the orbit. It's not interesting dynamically, but you can still form a quotient. And many of the structures that I want to discuss today will concern discrete groups, but that's not going to be enough to for the group action to be proper. In the case of hyperbolic manifolds, sometimes the manifold, the quotient, can be compactified by adding an ideal boundary, which is modeled on the boundary of hyperbolic space, which is a sphere, and that has a flat conformal structure, which I'll describe later in this talk. And that's an example of an Ehresmann structure where X is the sphere and G is its group of conformal transformations. The first paper I am aware of that Ravi wrote on this subject is in Journal of Differential Geometry in 1978, entitled The Principle of Uniformization. And let me say some words about that paper, since I think it was very important. After Ehresmann began the subject in 1936, I think maybe the next work was around 1950 by Kuiper, who studied things from this point of view and worked on conformally flat manifolds. Vinberg and Koziol studied affine and projective cones and convex sets in the 1960s. Benzacree, who was, I believe, a student following a student of Ehresmann, did work in the late 50s and 1960s and proved that the only surfaces that had met affine structures, closed surfaces, are those of the Euler characteristic 0. And the field moved fairly slowly in that time, but it contained many examples, as I will be describing. Ravi's work in this paper proposes this as a model for uniformization, in the same sense that the uniformization theorem for Riemann surfaces asserts that every Riemann surface has a natural spherical metric, Euclidean metric, or a hyperbolic metric. So it's in the spirit of uniformization that we are studying these geometric structures. The key point in discussing these structures in the pseudogroups are that, first of all, the local coordinate changes extend to globally defined transformations from G. This is why biholomorphic maps define a pseudogroup, but they are not in the class of Ehresmann structures. The other point is that a uniqueness statement, and that's that two transformations from the Lie group, if they agree locally, then they're the same. This means that the coordinate chart from one coordinate patch can be extended uniquely to a neighboring one. And by the first point, the global extension, the second coordinate chart can be dragged along. And this creates a development, in the sense of Elie Cartan, which is an immersion of the universal covering space of the geometric manifold into the model homogeneous space X. Furthermore, the deck transformations of the universal cover are represented by transformations in G, giving rise to a homomorphism from the fundamental group of the manifold into the transformation group G. And one simple application is that if the model space is non-compact, such as Euclidean space or affine space or hyperbolic space, and the manifold is closed, then the fundamental group has to be finite, be infinite. There's a typo there. The fundamental group of M is infinite. That's because the universal covering space, if pi1 of M is finite, it would be compact, and the developing map from the universal cover is an open mapping, but M tilde is compact, so the image would be both open and closed in X, which is non-compact, and connected. So this is a contradiction. This is kind of a maximum principle, because the globalization of the coordinate charts are the developing map. And such a map cannot have a local maximum nor a local minimum. So this proves the assertion that I made at the very beginning, that the sphere has no Euclidean structures. But this is much more general, because it would include other geometric structures modeled on non-compact homogeneous spaces, such as the hyperbolic space or affine space. So I'll say something about affine structures. A flat affine structure is a geometric structure modeled on Rn, which is affine space, but the coordinate changes are more general than just Euclidean isometries. They're just affine transformations, linear transformations composed with translations. If the linear part is orthogonal, then we have a Euclidean manifold. We've already discussed them, and they were classified qualitatively by Bieberbach. However, if the linear part is not isometric, then the notion of distance falls apart, but the notion of parallelism remains. And an affine structure in more traditional geometric terms is a affine connection of zero curvature and zero torsion. So those are some of the structures. I don't think I'll have time to give the classification, but in recent years, through the work of many people, in dimension 3, the affine structures which are geodesically complete, that is, ones that are quotient of R3 by groups of affine transformations, have been classified. And there's a good conceptual understanding of what they are. Let me discuss flat conformal structures. So in Riemannian geometry, the notion of conformal flatness can be interpreted and defined in terms of conformal classes of Riemannian metrics. So a conformal structure on a manifold is a notion of angle. So two Riemannian metrics give the same notion of angle. Say this would be an angle, but angles between tangent vectors at a single point. And two inner products give rise to the same notion of angle if they're a multiple of each other. Two Riemannian metrics on a manifold are just have the same conformal geometry if they differ by a scalar at each point, that is multiplication by a positive function. A flat conformal structure on a manifold is a conformal class of metrics such that each point has a neighborhood which gives the same local geometry as Euclidean space. And so, although it's not clear immediately that this is a geometric structure in the sense of Ehresmann, there's a classic theorem of Liouville that in dimension greater than or equal to 3, flat conformal structure is exactly a geometric structure modeled on the sphere and its group of conformal transformations. The reason is that any conformal map between open subsets of Euclidean space extends uniquely to a conformal transformation of the sphere, and therefore conformal structures in the Riemannian sense in this range of dimensions are the same as geometric structures modeled on the sphere and its group of conformal transformations. The group of conformal transformations is the special orthogonal group SOn+1,1, which is acting by Mobius transformations. One can see this by embedding the sphere as a quadric inside the n sphere as a quadric inside real projective n+1 space, and the group of projective transformations preserving the quadric identifies with the special orthogonal group. In Ravi's 1978 paper, he showed that there's a natural notion of a connected sum between two such manifolds. And there are a lot of examples of manifolds with flat conformal structures. in particular, all Euclidean manifolds, all hyperbolic manifolds, and all spherical manifolds admit flat conformal structures by embedding the model spaces conformally in the sphere. In case of elliptic geometry, it is the whole sphere, but a much smaller group. Ravi's construction shows that it's quite natural for, in three manifolds, to have conformal structures, and more general operations can give rise to flat conformal structures on manifolds that have incompressible tori. And however, the richness of the subject is that not all three manifolds do admit such structures. For example, the quotients of the Heisenberg group. My introduction to this subject was as a student in the 1970s with Bill Thurston, who put the geometrization program in the context of GX structures in the sense of Ehresmann. Thurston, in dimension 2, which is a good starting point, there are three geometries, the two-sphere, Euclidean space, and hyperbolic space. And every surface has one of these three structures, depending on the Euler characteristic. Dimension 3, the situation is more complicated, but Thurston proposed that every three manifold has a canonical decomposition, and this was known in three-dimensional topology, how to decompose a three manifold, and the building blocks he proposed would have one of 8 different geometries modeled on three-dimensional Riemannian homogeneous spaces. And so this will be a recurrent theme in this talk, in that certain classes of three manifolds, certain flavors, will have different kinds of geometries. But the geometries I'm discussing, such as flat conformal geometry, there is no conformally invariant metric. So the group G of conformal transformations of the sphere does not preserve a natural Riemannian metric, but there are metrics that are invariant under large subgroups, such as the orthogonal group, which is the group of isometries of the sphere. In the same paper, so the idea for the connected sum operation is that inversion of spheres, which is the way one conformally maps the inside of the sphere, the unit ball, say, to the outside, that's a conformal map. And using inversions, one can define a geometric construction of connected sum, which agrees with the topological construction. In general, and this is another part of Ravi's paper, is to look at various projective spaces over various fields. In that case, one gets a rich class of structures. For example, structures that are modeled on the complex projective line. Well, these have natural structures as Riemann surfaces, and these geometric structures have been studied since the mid-19th century from the context of Schwarzian differential equations. I won't say too much about that, except that they also appear in the theory of Kleinian groups, and where you have a discrete group of conformal transformations of the sphere, in this case identified as the complex projective line, and it has a limit set, which is in this case, the closure of the set of fixed points of elements, and the group is acting properly discontinuously on the complement of the limit set. And these complex projective structures often will appear as ideal boundaries of hyperbolic 3 manifolds. And as Liouville's theorem doesn't hold in dimension 2, but the complex projective one-dimensional structures are the natural analog of flat conformal structures in this dimension, real dimension 2. In Ravi's paper, he identifies the quaternionic projective one-dimensional structures exactly as the flat conformal structures in dimension 4. And this is, I find, quite fascinating that there's this whole world of geometric structures modeled on the quaternions and other algebraic structures. Let me now turn to another class of geometric structures. As I mentioned, Thurston's picture of 3 manifolds is that up to the canonical decomposition, then there are 8 different geometries. And so there's spherical, the 3 Riemannian geometries of constant curvature, Euclidean geometry, hyperbolic geometry, and the sphere. Then there's the product geometries, like the sphere cross a circle, hyperbolic space cross a circle. Then there's the geometry, two geometries of quotient of the Heisenberg group. So those correspond to non-trivial circle bundles over the torus. And then also hyperbolic torus bundles, which are going to be a mapping torus of hyperbolic automorphisms of the torus, elements of them GL2Z. So those are the 8 geometries. And in Ravi's work with Frank Raymond, 1985, they showed that a closed manifold which admits a structure of constant curvature Lorentz metric has to be one of this interesting geometry of anti-de Sitter space. So let me say a little bit about this. One of the features, so now let's replace the Riemannian metrics by indefinite metrics. And so let's assume that X is a Lorentzian manifold and assume that its group of isometries acts transitively. So this gives rise to a geometric structure in the sense of Ehresmann. However, the situation is much more complicated because even if you assume a subgroup of isometries is discrete, it may not act properly. In particular, there's no guarantee that the quotient space is a Hausdorff manifold. And a fascinating case, which is beginning to be understood, but there's still many open questions, is the analog of hyperbolic space, where the Lorentzian manifold has constant curvature -1. This is sometimes called anti-de Sitter space. In dimension 3, there's a very nice picture in terms of Lie groups. Namely, take X to be the Lie group SL2R. Actually, maybe it's better to take its universal covering space. And then SL2R acts on itself by left multiplication and by right multiplications. And the killing form on its Lie algebra has index 1 and defines a bi-invariant metric, Lorentzian metric, on SL2R. So this is one way of getting lots of examples of homogeneous spaces and geometric structures, is but to take a Lie group and look at and take that as the space X, and then take take for the structure group of the geometry, the Lie group cross itself. And in very important paper in 1985, Kulkarni and Raymond showed that if a closed manifold of dimension 3 has such a anti-de Sitter structure, then it must be a Seifert manifold with hyperbolic base and non-zero Euler number. So a basic and fundamental example of this is to take a closed hyperbolic surface and take M to be its unit tangent bundle. And this has many rich structures. Conversely, they showed that any three manifold in this class, any three manifold in this geometry in the sense of Thurston, it admits such a structure, a special kind of structure they call standard, and that corresponds to a left invariant Riemannian metric on SL2R. And this is the model space for that geometric structure in Thurston's geometrization program. Now a theorem due to Perelman. So as you can see, there is a rich class of discrete groups. Basic question is, when does that discrete group act properly? And the nicest situation is the classical theory of Kleinian groups, whereby the closure of the set of fixed points on the boundary, the sphere, has is an invariant closed subset called the limit set. And a remarkable fact in hyperbolic geometry is that the group acts properly on the complement of the limit set. And so Ravi had studied this and generalized it, and I'll just mention one notable theorem that Ravi and Peter Shalin proved, gave topological proofs of some of the classic theorems that used, the original proofs used automorphic forms, but they got to the heart to see that these were really topological in nature, namely the all-force finiteness theorem, that the region of discontinuity for a finitely generated Kleinian group is Riemann surface of finite type, and Beers's area inequality, which gives a bound for the topological type of the quotient. But for more complicated geometries like projective geometry, just because the group is discrete, the action is not necessarily proper, and this becomes a central question in the subject. And in a series of papers in the late 70s, Ravi showed that there were a whole hierarchy of limit sets, starting from the closure of the set of fixed points, that's the smallest one, to the largest one, and which is actually somewhat ambiguous, but on one of these, the quotient will be acting properly. I might just mention that this is developed into a huge area of research sometimes called higher Teichmuller theory. One result that I'll mention is that Olivier Guichard and Anna Wienher recently showed that a general notion of Anosov representations due to Francois Laverie, which generalizes the convex co-compact Kleinian groups in rank 1, admit domains of discontinuity, namely regions on homogeneous spaces, quotients by parabolic subgroups, such as projective spaces, such that the quotient is a compact Hausdorff manifold. And a geometric approach to this subject was also independently found by Misha Kapovich, Bernhard Lieb, and Joan Porti. Let me close by describing another fundamental set of contributions Ravi and Ulrich Pinkhall, and that is in a pair of papers, one in 1985 and one later in 1994, discussing geometry on flat conformal manifolds. So in general, when you have a homogeneous space, that the group might not preserve natural notion, a metric space structure. It may preserve angles. In the case of a conformal structure, for affine structure, it doesn't preserve angle or distance, but it will preserve a notion of parallelism, notion of geodesic, even though the notion of the speed of a geodesic is undefined. The notion of zero acceleration makes sense. Or projective geometry, where you don't even have affine parameterizations of geodesics, but you do have a notion of incidence. And so a theme in this subject is to find refined structures given one of these large homogeneous spaces. And so in these two beautiful papers, Kulkarni and Pinkel show that in general, a conformal geometry has a natural notion of a metric, which in dimension 3 was a part of Thurston's picture of the convex hull of the limit set as being a convex pleated surface inside a hyperbolic 3 manifold. So the picture is that of a hyperbolic space that's bent along a family of geodesics called the geodesic lamination. And this is very similar in spirit to the construction of Kobayashi of intrinsic metrics, pseudometrics on complex analytic spaces. And the key point in Kulkarni, Pinkel, and also in Thurston is to find maximal balls inside the universal cover and use their geometry, like in particular the Poincare metric on the ball, to describe a geometry on the developing. The whole problem with the developing map is we saw one application of it to show that closed manifolds of finite fundamental group do not admit geometric structure modeled on non-compact manifold, but in general, it's not a whole lot of information to work with, aside from the sort of maximum principle to which I earlier alluded. And so, in general, the developing map can be quite wild. Even if the manifold's compact, it may not be a covering space onto its image. And the Kulkarni-Pinkel theory is very similar to another result of this around that time, and in the same spirit, of David Fried, who classified manifolds that are modeled on Euclidean space, but where the structure group isn't the group of isometries, but somewhat larger, namely the group of conformal transformations or similarity transformations, such as dilations. And Fried and independently Ehresmann prove that every such manifold with this geometric structure is either a quotient of a flat torus, that is a Bieber-Balk Euclidean manifold, or it's covered by a Hopf manifold. So these are quite interesting manifolds. These were first discovered by Hopf as examples in the complex case of compact complex manifolds that aren't Kähler, but these admit natural affine structures too. So you take Euclidean space, remove the origin or any other point, and then a group of linear expansions fixes the origin, but we've removed it, but it acts properly on the complement. A fundamental domain is a spherical shell. Say if the dilation is multiplication by 2, it would be the region between the unit ball, the unit sphere, and the sphere of radius 2. And so Fried showed this, actually Kuiper had announced this back in his work in the 1950s, but there was a gap in the proof. And Fried and Ehresmann show that that any manifold that's modeled on this larger group of similarity transformations has these two refined geometries, either Euclidean geometry or this Hopf geometry, which is one of the Thurston geometries of dimension 3, S2 cross S1. Freed's proof uses a detailed analysis of the boundary of the universal cover, and this is exactly the analysis that goes into the Kulkarni-Pinkel theory in their 1994 paper. And so there's another result too, which I don't really have time to mention, of Ravi's, which I also think is very important and very imaginative, and that's an extension of the Riemann mapping theorem for Lorentzian manifolds in dimension 2, Lorentzian surfaces, which has seen a lot of further developments. And it uses a lot of these ideas that are of understanding domains, the boundary behavior. The last thing I want to mention is in the first paper of Kulkarni and Pinkel, and that's an extension of the notion of normal families of Montel, which, for example, can be used to prove the Riemann mapping theorem. And the theory that they develop is very important technically to control the developing maps. As I mentioned, that typically the developing maps are not covering spaces under their image, and using Ravi's connected sum construction for conformally flat manifolds, one can construct flat conformal manifolds whose developing maps are onto the whole sphere. However, if you have a conformally flat manifold, then and the developing map is not onto, then it's actually a covering space. And in fact, the manifold is a quotient of a Kleinian group, as in the traditional case. So the proof is a basic lemma involving normal families, and the construction for pathological developing maps is a grafting construction, which I don't have time to go into. But basically, the idea is to take two manifolds with geometric structures and glue them together, similar in spirit to the connected sum operation I described before. And this, I had written a paper where I show that projective structures whose holonomy homomorphism is a Fuchsian representation is obtained by taking a hyperbolic surface and grafting along tori. However, there's a gap in my paper which can be filled, and one of the nicest ways of repairing it is to use the basic lemma that Ravi and Ulrich used in their discussion of normal families. More recently, this fact was used by Serge Dupont in his PhD thesis in 2003 as a key step in classifying the projective structures on hyperbolic torus bundles. So a hyperbolic torus bundle is a three-dimensional solved manifold. That is, it's a quotient of the unimodular non-nilpotent three-dimensional Lie group. This is one of the Thurston geometries called Sol. And these are manifolds that are quite interesting. So like the manifolds I mentioned, Thurston geometry, the unit tangent bundle, or SL2R geometry, these geometries have natural geometric Anosov flows on them, and they're quite interesting and complicated. Dupont proved that every such projective three manifold, homeomorphic to a hyperbolic torus, is a quotient of all of affine space R3, a half space, or one of the regions bounded by a parabolic cylinder. The key point is to use the normal families lemma to show that the developing map misses lower dimensional invariant submanifolds invariant under a Lie group that naturally contains the holonomy group. And so this is the way the developing map is tamed, and I think these ideas are just beginning to be used, and I find this a very exciting field, and I am quite happy to congratulate Ravi, wish him happy birthday, and many more, and lots more mathematics and the subject of locally homogeneous geometric structures. So congratulations, Ravi.
Thank you. Yeah, Bill Goldman is today's world's expert, and he has written many books on the subject and guided many students, and really developed the subject far beyond what I was considering. Thank you, Bill.
Thank you.
Thank you, Professor Goldman, for a nice talk. So I'd like to ask anybody if there are questions. Professor Mukutmani Tripathi.
Hello, Professor Goldman. Have a nice time, please. Can you hear me?
Yes, I can.
Yes. I was studying the Thurston classification. It's in his book in 1997 about three-dimensional connected geometries, Riemannian geometries. So there are exactly 8 models there. And what is surprising, I'm just adding something to your lecture. It's nothing like that, because I try to work in contact geometry as much as possible. So because of a paper appeared in 2009, so every connected three-dimensional, Riemannian manifold, it carries an almost contact structure. Not exactly contact structure. If the three manifold is compact, then it always carries a contact structure. It's well known. But even if it is not compact, still it has an almost contact structure. It means whose structural group is reducible to UN cross 1. UN cross 1 unitary group n. The dimension of the manifold is 2n plus 1. And interesting fact is that in all these 8 model spaces, the 7 spaces, they are normal. Normal means when we take their product with real line, then the standard almost Hermitian structure, it becomes Hermitian. It becomes integrable. But the only one, the sole 3 space, it is not normal, and its geometry is not well known. I don't know if it is something known about this geometry. I just wanted to inquire that if it is really not studied much, then maybe I can take up this study, because being non-normal, a lot of theories could be new in this case. Sir, your comments.
I think that would be really interesting, actually. One of my favorite geometries that I've been thinking about is RP3 structures, with a natural contact structure. So the holonome lies in the symplectic group, SP4R, and that preserves a natural contact structure on RP3. And so I don't know what the structures on hyperbolic torus bundles would be, but this includes many examples. And I've wondered if there is a notion of grafting in this context. I don't know if that's related to your question about the almost contact structures, but it seems like the techniques of contact geometry should be applied to some of these geometric structures in dimension 3.
Thank you.
Anyone else has a question? Professor Ajit Idwal Singh, I see there is a message from you. Would you like to ask some question to him? Yeah.
No, it is a layman's question that set of fixed points is closed. But you said that you will take closure of the set of fixed points. So is it in some larger space, or why do you do it?
Well, these are the fixed points of individual elements, and the groups are infinite. They're countably infinite. So this for a single element, the set of fixed points is closed, but I'm taking the union over all the elements. And so that will not be closed, and the limit set is the closure of the set of fixed points of all the elements. And that'll be it's a countable dense subset, like the rationals and the reals. And so I think that's the answer to your question. When I said the set of fixed points, I meant the set of fixed points of the union of the fixed point sets of all the elements. And that generally will not be a closed subset. And so the minimal, that's the minimal limit set in Ravi's sense, is that you're not going to get a proper action when you're at a limit point of fixed points. But in higher rank, you have to remove even more to get a domain of discontinuity.
Thank you. That negation of a truth is a more profound truth. You are giving confirmation of that.
Okay.
In a larger context, the accepted truth in a smaller context becomes wrong. So my conception was wrong because I was in a limited context. Thank you.
You're welcome.
Okay, so if there are no other questions, let's thank the speaker again. Thank you, Professor Goldman. So we'll be moving.